All right, so in this video, we're going to talk about how to use the activity series. And then we're also going to talk about combustion reactions. Okay, so you're going to need your solubility rules table, and we're actually going to be using this part of it right here, which is actually separate from the solubility rules table. It's called the activity series. So everybody in class, I said, hey, let's write down single replacement only, just to remind ourselves that this activity series we're only going to use for single replacement reactions. And then I hand wrote in plus, minus. That's just to show you that these are two separate columns. Excuse me. So there's a positive column, there's a negative column. All right, so let's show you how to use this. So this is only for single replacement reactions. So in single replacement, remember we have an element and we have a compound. That's how I know it's single replacement. So this element right here is always going to try and switch places with something. And it just depends on whether it's positive or negative. If you remember, the element, let's say it's positive, it's going to switch with something else that's positive. So similar charges switch places. If my element was negative, then it's going to try and switch places with the negative part of the compound. So single element must be more reactive than the element it's trying to replace. Okay, so let's just see what that looks like. So I'm going to do the first reaction here. Silver, Ag, plus sodium nitrate, NaNO3. I'm going to draw my arrow. Okay, so the element silver is going to try and switch places either with the sodium or it's going to try and switch places with the nitrate. So in this case, sodium's positive and silver's positive. So those two things are going to try and switch places with each other because they're both positive. So silver's going to try and come in and kick out the sodium because it wants to bond to the nitrate. So what we want to know is, can silver come in and actually kick out the sodium? And how you do that, how you figure that out, is you come over to the activity series. And the activity series is all based on the higher up you are on this table, the more active you are, or the stronger you are, or the more reactive you are. So lithium reacts with everything, gold reacts with nothing. All right, so silver is right here, and sodium is right here. So sodium clearly is stronger than silver. It's much more active. So then if I come back over to my example and I look at, can silver come in and kick out the sodium? No, it cannot, because silver's way down on the bottom and sodium's way up here. Sodium's stronger. It's more active than silver. So silver cannot come in and kick out the sodium. So that means this reaction does not take place, and so we just put NR for no reaction. Okay, because silver cannot come in and kick out the sodium. So let's look at another one. Zinc plus sulfuric acid, H2SO4. And I want to know, can zinc come in and replace the hydrogen? I know zinc is going to try and kick out hydrogen because zinc is positive and hydrogen's positive. So I want to know, can this zinc come in and kick out the hydrogen and bond to the sulfate? Again, if I go over to my solubility rules and I pull up my highlighter, let's use a different color now. Okay, so let's use green. So zinc is here and hydrogen is here. So zinc is actually higher than hydrogen on the activity series, meaning zinc is much more active. So that means that zinc actually can come in. It can swoop. Where were we? Zinc can actually come in and remove the hydrogen. So if that's the case, then we're going to write zinc sulfate, because zinc is +2, sulfate is -2, and hydrogen is now going to be by itself. Hydrogen is part of Brinkelhoff, so it gets a 2. And I'd balance it, but it already looks like the equation is balanced. All right, so if we did another one, let's do this last one here, copper. Cu plus hydrochloric acid, HCl. All right, so copper is going to try and switch places with hydrogen because they're both positive. If I come back over here, I want to know, is copper higher than hydrogen? Well, let's see. Copper is here. Hydrogen is there. Even though it says H2, it's still hydrogen. So copper is lower than hydrogen on the activity series. So copper is less active or less reactive than hydrogen. So copper cannot come in and kick out the hydrogen. So again, we're going to put no reaction. All right, so that's how we use the solubility rules. Okay, now I'm going to expand this so we can get a little better view. And the last thing I'm going to talk about is combustion reactions. Now, combustion reactions look like this. Dicarbon, C2 hexahydride. So let's see, C2H6 plus O2 yields something. And then the next one, carbon tetrahydride plus O2. And then if I did one more, propanol. I don't expect you to know what the formula is for propanol, so that's why it's right there. It's C3H8O plus oxygen O2. Okay. Now, if we take a step back and we look at, well, what's the same about all of these? So they all have an oxygen in the reactants, and they also have some sort of hydrocarbon. All right, and hydrocarbons are anything that has carbon and hydrogen in it, oddly enough. Very creative name there, hydrocarbon. So it can also have oxygen in it like propanol, but it has to have carbon and hydrogen. So if I see any compound or any reaction that has a carbon and a hydrogen and it's reacting with oxygen, I immediately know this is a combustion reaction. Okay, this is the fifth type of reactions. All right, so we have synthesis, decomposition, single replacement, double replacement, and now we also have combustion. So we're going to have to indicate what type it is. Hydrocarbon plus oxygen, I know it's a combustion reaction. Now the cool thing about these is they produce the same thing every single time. So once you identify, hey, this is a combustion reaction, the products are really easy to predict because it's the same two products every single time. Every time? Yes, every single time. CO2 and H2O. So they're the easiest ones to predict the product. Okay. Now, sometimes they can be a little tricky to balance. So that's where we need to come in and just make sure that we understand how to balance these equations. All right, so I'm going to balance the carbons first. There's 2 on the left, so I need to put a 2 right there. Now I'm going to balance my hydrogens. There's 6 on the left, so if I put a 3 right there, that gives me 3 times 2 is 6 hydrogens. Now if I count my oxygens, I have 2 times 2, so I have 4, and I have 3 times 1, so I have 3. So that's 4 plus 3 is 7. There's no number I can put in front of the oxygen and get 7. It can't happen. So if you guys remember, the trick here is, well, if I go back and I double this, and then I double this, so instead of 2, it becomes 4, and if I double this, instead of 3, it becomes 6. Now 2 times 2 is 4 carbons, 4 carbons, 6 times 2 is 12 hydrogens, 6 times 2 is 12 hydrogens. Now my oxygens, 4 times 2, so I have 8 oxygens here, and I have 6 times 1, I actually have 6. So 8 plus 6, that gives me 14. Now I can go back and I can put a 7 right there, and now I've balanced the equation. So, combustion reactions, hydrocarbon reacting with oxygen. They will always produce the same thing every time, CO2 and H2O. Sometimes they can be a little tricky to balance, and if that's the case, you just multiply everything by 2 and then balance your oxygens, and they usually will balance out.